Welcome back to the Software Screw Up series. I'm Dick Seitz. Today's episode 5 is on critical section locks. The problem with critical section locks is, as an industry, we don't have any good observation tools. So this is a page from my book on understanding software dynamics, which mentions that there's no broad brush tools, low overhead tools, or that pthreads doesn't have a designed-in tracing facility, or that some of the techniques that people use instead are too slow to be used for 100% of the locks, that you only instrument a few locks and hope they're the ones that you care about, but often, of course, they aren't. Locking is hard. Locking problems are hard. It's especially hard if you have thousands of locks. About 10 years ago, when I was working at Google, I did a search of the entire Google source code base for declarations of locks. I found about 135,000 locks declared. So one of the big problems you have in a big software system when you realize that you have some problem waiting on locks too long is you have to figure out which lock. You have to design in being able to find that. It's hard to do, for instance, if the data structures for waiting for locks all involve dynamically allocated memory and linked lists and things. And so the addresses involved don't mean anything about which real lock is the problem. And it makes it very difficult to get your way back to some line of source code that declares or uses the lock. So here's a quick overview of an uncontended lock on the left. You get the lock, go into the critical section, free the lock, you're done. For a lightly contended lock, one process may try to get the lock and fail to get it, wait a little while, try to get it again, get the lock the second time, do the critical section, and leave. When you have a heavily contended lock, there can be multiple processes that fail to get the lock, wait a little while, fail, and loop. You don't want to do that forever, or you'll tie down a whole CPU core just spinning, waiting to get a lock. So after a while, it's worthwhile to block, go to sleep, free up the CPU, let other programs run, and then eventually when whoever holds the lock frees it, get woken up, try again to get the lock, and if you fail, go around the loop and keep doing this several times until eventually you get the lock, do the critical section, and free the lock. So if you want to build an observation tool, what do you need to observe? Which locks are you waiting on? Who's holding them? And why are they so contended? So for example, in the uncontended lock case, you don't want to add any observation tool, trace points or anything. This is the normal case. It's fast and you want it to stay fast. You don't want to slow it down. It happens all the time. In the contended lock case, you are going to wait a little while. And so making that process slightly slower by adding some trace information when you fail to get a lock probably doesn't change the time in any measurable way at all. So you'd like to have a trace point when you fail to get a lock, a trace point later when you actually do get it, so that you can look at the two timestamps and see how long you're waiting. And when you free a contended lock, you want to timestamp that and which process is freeing the lock, because there's some other process over here waiting for it that you'd like to know if process A is holding a lock and process B is waiting. The symptomatic problem is that B takes too long, but the fix is going to be in A holding the lock too long, or in the grabbing the lock, which we'll talk about near the end. In a heavily contended lock, you fail to get the lock, you wait a little while, you fail and loop, you eventually go to sleep, you eventually wake up, you fail and loop again, you go all the way around. The thing to instrument is when you first tried to get the lock and didn't get it, and when you finally got it. And then for a contended lock, when you free a contended lock, to record that you're the one who's freeing it and what time. Okay, if you do that, what you need to do at each trace point is to record the timestamp, which event it was, fail, get the lock, or free the lock, who is dealing with it, who is failing to get it, which process, or who's freeing it, which process, and of course, which lock. If you record those four things, that's enough information to reconstruct which locks are problematic, how long the losers wait, and which processes are holding the locks, causing the long waits, and hence why. In the case of starvation, as we saw in a previous episode with the drinking philosophers, if you're waiting for a long time because other processes are getting in and out, and every time you go to get the lock, you fail, what you'll see during this time is all of the freeze implemented by the processes that did get the lock and then freed it. And that gives you a strong clue about how the starvation dynamics are really happening. Okay, and finally, for bonus points, consider recording for each lock a small histogram of the fail until you finally get elapsed times per lock, and compare that to a programmer's estimate of the 90th percentile waiting time. If you ask programmers when they declare a lock to put in some number of microseconds of how long they think the lock's going to take to get, in the not absolute worst case, but the 90th percentile slow case, and you then record a histogram and calculate the actual 90th percentile now and then, you get to find places where the programmer's estimate of how long a lock is held is way off by 1 or 2 orders of magnitude. But there's a lot of learning there, both for programmers and for redesigning the locking structure at that point if the estimate is for a contended lock that's actually causing performance problems. So that's it on the observation tool design. Thank you for listening to and watching the Software Screw Up series. Take care.